It is a great pleasure for me to introduce Guy Worthey. He's associate professor in our department, of course, and so he wouldn't really need an introduction. So I just dig through his past and I'm unearthing some of the lesser known facts about him. So Guy actually grew up in Casper, Wyoming, which is an outdoor lover's paradise, famous for Mount Casper, brutal summers and brutal winters. But not too surprisingly for an outdoor town, Guy actually started his career out with an associate science degree in geology from Casper College. So today it's also probably some connection to geology in there. Yeah. And then he soon switched from Earth to more far-reaching aspirations, reaching out into space. He got his bachelor degrees in astronomy from the University of Wyoming, and his master in science and PhD in astrophysics from the University of California in Santa Cruz. So from Santa Cruz, he got his PhD in 1992 with a thesis titled "The Controlling Parameters of the Integrated Flux of a Stellar Population." And at Santa Cruz, he actually was working with Sandra Moore-Faber. She's a very, very famous astronomer. She's, of course, well known for the Faber-Jackson relation and also for her work on the design of the Keck telescope. The Faber-Jackson relation provided the first empirical power law, a relation between luminosity and the central stellar velocity dispersion of an elliptic galaxy, right? Got that right. Okay. So from 1992 to 1994, he was a lecturer at the University of Michigan. And then from 94 to 97, he was Hubble Fellow at the University of Michigan. Hubble Fellowships are awarded to outstanding postdoctoral scientists whose work relates to the mission directives of the Hubble Space Telescope. And nowadays also the James Webb Telescope, the Stratospheric Observatory for Infrared Astronomy, SOFIA, and the Spitzer Space Telescope. And only a handful of those are actually awarded each year. Of course, the University of Michigan is a famous place. And just as a fun fact on the side, some 20 years later, actually a graduate student by the name of Vivian Baldessari got her PhD from the same place. Okay, because she went on to Yale as the Einstein Fellowship. So from 97 to 2001, Guy was assistant and associate professor at St. Ambrose University. And since 2001, he's here at WSU with us. His research interests are stellar populations, observational cosmology, and galaxy formation and chemodynamical evolution of the universe. According to ResearchGate, Guy has about 150 publications and over 10,000 citations. Now that's a really big number. It's 4 zeros. Yeah. So he's actually very well known for his stellar publication record, but also for his very, very entertaining presentations. And in the time when he temporarily escapes the gravitational pull of stars and galaxies, he actually writes fiction. So you'll find books from him on Amazon. Okay, so we are very happy to have him here to talk today on terraforming the moon.
Thank you, Peter. Good to see you all. It's nice to see shining faces and all that. It's very, very much a pleasure to be here. It's completely accurate. All that stuff is very, very well researched. Before I talk about the moon, which of course is way outside my field, so if there are experts on terraforming here, I'm just I don't want to. That's true. But I will extol the virtues of undergraduate level physics as this talk commences. Before I do that, though, we have already a malfunction. Maybe. Let me just recap my group real quick, and my field really is stars and galaxies. So I want to know how galaxies form, and I take stars as helping tools to make that happen. So I try to figure out ages and metallicities and abundance ratios and star formation histories of galaxies using stars. And a recent student is Islam Khan, listed here, and his thesis was on a new variant of the inflation model for the cosmological beginning of the universe. And he took that model and he pushed it all the way to predict things like gravitational wave signals and so forth. So that was pretty far outside my field, but it was fun to ride his coattails on that. And two current students are Tatagata Paul and John Sheep. Tatagata is working on mostly stars. He's discovered some ages for carbon stars in the Milky Way galaxy. And he's about to publish a big library of HST spectra of stars. So that's a exciting development. John is working on a new age dating technique. He's using chemical peculiarities in stars to trace the ages of those stars if they appear in galaxies. So a good vibrant group going on right now. All right, so let's talk about undergraduate physics and Mars and the moon and other things that I don't specialize in. Just have to slip that disclaimer in there. Mars, of course, is a ridiculously popular place. All kinds of craziness goes on when people talk about Mars, and Mars has been cast as for the name Mars comes from Greek mythology. I guess Ares is the god of war, and then the Roman version is Mars, the god of war, and it's just gotten stranger since then. Percival Lowell thought Mars had canals that drew water from the north and south poles to the equator, and he said, "Oh, this must have been built by a civilization, and Mars must be dying, and they must be trying to get water to keep their civilization alive." And so it went. We always populate Mars a lot. It is a romantic place, and the geologists now know that Mars used to be wet. So 4 billion years ago, it probably had an ocean that covered the entire northern hemisphere of the planet. And it had an atmosphere thick enough to keep that water liquid. And from there, it dried out and it cooled off. So if Mars used to be clement, could it be that way again? This is kind of a question about Mars. So science fiction writers love Mars, and they love to write stories about terraforming Mars. And that word just means making it habitable to humans. And the latest on the bandwagon you might know is Elon Musk. He says that he'd like to terraform Mars. And part of his plan, besides nifty videos and stuff, is to explode thermonuclear weapons over the north and south polar caps to volatilize the carbon dioxide and make it into an atmosphere. The trouble with that plan is it doesn't work. Even if it stayed hot, and even if you could heat it all up, it's still not a very thick atmosphere, and it does not become self-sustaining. So the amount of carbon dioxide there is not enough to overcome the greenhouse, give enough greenhouse effect to keep it in the atmosphere. And it's still pretty low pressure, very low compared with one atmosphere. So what does it say? I'll calculate the pressures and stuff pretty soon with undergraduate physics. So basically you're left with, okay, some CO2 in the atmosphere, but it's still cold, it's dry. If you introduce water, that water is all just gonna evaporate into the atmosphere or freeze. So you're still left with an airless, cold Mars. You could maybe get some more CO2 by digging for it, so there might be plenty underground. But, okay, if we're gonna start just digging stuff up on Mars and then making atmospheres out of that, why not consider the moon? So the moon is a lot closer and favorable in certain ways as well. So here's just the size comparison. Earth, Mars, and the moon. we'll get to calculating the basics here, but of course, that's kind of how things work. Did I skip a slide? No, okay, good. Well, here comes a little bit of undergraduate physics. These sizes also have densities and we also have gravity. So let's figure out surface gravities first using, yes, undergraduate physics. So what we do here is we use Newton's gravity law and we set that equal to mg. So g, of course, is the special acceleration that we feel on the surface of a planet. So F equal ma combined with F equal gmm over r squared. So we do that. And the model that Newton came up with, of course, is two masses. So one's capital M, one's little m, and then you got the distance between them. So those are the parts of the model. But of course, you can take one mass and make it small, like a test mass, and then you make the other one really big, and then you can keep the distance between them even until it touches the surface there. And that's the radius of the planet at that point. And at that point, we can call it little g, the surface gravity of the planet. The little m's here do cancel out. And so you can just sort of divide those out and you get g is big G over r squared. G, of course, is the gravitational constant. I hope through this talk that everyone here feels this glow of familiarity, this comfort of, yes, I do know physics, actually. So if we work through the masses of the planets, we find out using this formula that, that the gravities down here on the bottom, so we have 9.8 meters per second, a number seared into your consciousness. And then for Mars, it's about a third, and for the Moon, it's about a sixth of that. So, so those are the parameters for surface gravity, which comes into all of the subsequent calculations. So let's go back to the pros and cons of Moon versus Mars. First of all, the Moon is closer, but let's drive in how much closer. The Moon in light travel time is 1.25 seconds away. Mars at its very closest, if you happen to be at close approach and that close approach happens to be in the month of August, then you're 3 light minutes away. If it's any other configuration, you're much farther away. And you can be as much as 22 minutes of light travel time away from Mars. If you're going to take a rocket there, it takes a few days for the Moon. It can be a fairly leisurely trip. For Mars, it's 9 months, and there's not a lot that you can do about that. Energy requirements for making the trip shorter are quite steep. And let me explain how that works. So here's a picture. You got the sun at the center. The first circle out is the Earth orbit. So that's the 1 year Earth orbit there. And then this is Mars. Mars' orbit here. So to transfer from Earth to Mars, what you need to pick is an orbit which is elliptical, that has a perihelion, close approach, at the Earth's radius from the sun, and then an aphelion at Mars's distance from the sun. And that's the lowest energy way to do it. And it's what happens is at Earth, you fire off some rockets and give your spacecraft some velocity to put it onto this elliptical orbit, and then you wait. So that orbit just climbs and then finally meets Mars here about 9 months later. And then you need to either brake by skimming the atmosphere of Mars, which is a trick that NASA has sometimes pulled off successfully and other times not. Or you just fire rockets again, just let's speed up actually, to speed up even more when you get to Mars. And there's not a lot you can do about this configuration, which recurs. So it takes 9 months. So sure, you started out here, but by the time you get to Mars, Earth has gone around and it's past there and it's over here. And furthermore, the configuration to start does not recur. I mean, it recurs periodically, but those periods it's over 2 years. It's 780 days apart. So you can only shovel a bunch of stuff at Mars every couple of years. Crazy stuff. Mars also gets less sunlight than we do. It does have a nice day. It's a 24-hour day, and that's a lot better than 709 hours for the moon. So the moon takes a month to go around. So that means daytimes are going to get toasty, and then night times are going to be very cold on the moon. So that's a definite demerit for the moon. But if you look at the amount of sunlight and the deficit of temperature, so right now Mars is about minus 65 on average. We need to get up to Earth temperatures of sort of 10, 15 Celsius. So we're looking at about 80 degrees of greenhouse effect that we need for Mars, with only 40% of the sunlight. So it's hard. It's actually a hard problem to get that much greenhouse effect on Mars. Moon, not so bad. We're almost there already. We just need a few more degrees to make it really pleasant. All right, so let's explore the following. Let's see what happens if we can terraform the moon. And the first thing we need is air. I guess the second thing we need is water. So let's see if we give the moon some air, and we'll see how long that holds up. And so let's explore this issue of the mass of the atmosphere. So how difficult it is to make that much air, and then will that air stick around on the moon once we have made it? So on we go into undergraduate physics. And what are we going to do first? Force balance. So let's suppose we had an air. So let's make an imaginary slab of air. And it's going to have some thickness. So let's make a coordinate, the z coordinate. So let's go upwards is z. Gravity is pointing down. So that's this area here. And then this slab will have some area, top and bottom. And then the distance, the thickness will be a dz. And then we're looking at the pressure difference. So between top and bottom, that's going to be a dp. Pressure is force per unit area. So we're just going to balance the forces going forward. So what's mass? I just feel that glow of, this is good stuff, isn't it? That sympathy. So mass would be density times volume, right? And so that's going to be the mass in that formula. And then you just balance the arrows. So the down pressure is, do this. Down pressure is pointing down, the up pressure is pointing up. So you oppose those guys. And then you add, pointing down, the mg factor. And then the mass is density times volume. And so I substitute there for the mass, I substitute the density times the volume, which is the area times dz. And then there's an A, and an A, and an A. So we can divide those out. Doesn't matter. And then this P up, P down, let's just make that a dP, shall we? So the final equation after canceling is dP is minus root of GBZ. And this is the hydrostatic equilibrium equation for fluids and solids and everything else. It's pretty general. That minus sign, of course, indicates that our coordinates going up, but pressures increase and going down. So there's a minus sign in there for that reason. Okay, that's great. We'll put this in a box. That's hydrostatic equilibrium. We need one more thing, and this is the ideal gas law, which relates to density and pressure. So we will need this tool. This particular form, I don't think anybody uses it really. It's a mix between the physics version, which P is NKT, and the chemistry version, which has an R in it. R is the gas constant in mole units. And written this way, with that in mind, you got you got rho RT from mu. Mu is the mean molecular weight. So how much does 1 mole of material weigh? And we're interested in that lovely molecule O2 as we breathe it. And the mean molecular weight of O2 is that number there, 0.032 kilograms per mole. Now let's differentiate that. So let's just dp it. And there are 2 things that could vary in there. We've got density, which might not be constant. R is definitely constant. T, however, could be also a variable. So let's do that by parts. So if you do it by parts, you get 2 terms. However, we're about to assume that we're going to have an isothermal atmosphere. So we're going to keep temperature constant. So we actually don't have a dT. So we're going to drop that second term. And so back to hydrostatic equilibrium, let's put these together. We put dP is this minus rho g to z. And we put this differential of pressure in there. So dropping that dT term, we put the rest in here with the mu on the bottom. And then you juggle it, you solve it for like terms on either side. You get d rho over rho on the left, and you get things which are almost all constants except for the height, dz, in there. Fun, let's throw integral signs around it. And let's assume that we're going to have a starting place. And our starting place will be z equals 0 and rho equal rho naught. So that'll be our starting place for our integral. And so we'll go from rho naught to a target height z and then a target density. We'll try to figure out what that is when we do the integral. These are excellent integrals here. This is the natural log function, the anti-log, and then there's only a dz here. I think I forgot the dz, put the dz, sorry. Typo. So the solution is this ln rho minus ln rho naught is minus mu dv over RT. Isn't this like, it feels good, doesn't it? It's like, yes, I can follow every step of this. And then you take both sides to the e power, and you get this. You get rho naught times e to the minus mu dz over RT. Okay, so most of those things are constants, or at least somewhat constant. What's usually done at this point is the oft-seen physics trick of taking some alphabet soup and just defining some constant. In this case, the constant we want to define is called the scale height, given capital H. So let's define scale height as most of those constants, RT over mu g. And then our isothermal atmosphere solution becomes really tiny. It's just e to the minus z over h, where h is all this stuff. So that's actually important though. The scale height is a measure of the atmosphere thickness. And so right away, just by calculating things regarding the scale height in terms of little g for gravity and so forth, and mu is the other one, then we can learn some things about what sort of atmosphere we're going to have. And temperature, well, we want that to be sort of room temperature-ish. We kind of want to set that temperature. So if mu is small, let's just do the hydrogen experiment here. If mu is 0.02, that's small compared with oxygen. It's 16 times smaller. And so if we compose the atmosphere of hydrogen, we'd have one that's 16 times thicker than one of oxygen. Kind of fun to think about. And then gravity also has, in fact, if the lunar gravity is a sixth of terrestrial gravity, then you're going to have 6 times taller atmosphere on the moon. So it bears in mind that, okay, you got a smaller moon, but the atmosphere in comparison is going to be quite thick in comparison with the Earth's. Okay, let's figure out, we've got to structure the atmosphere. We know the vertical structure now. Let's calculate the mass of an atmosphere given a planet of a certain size and a certain gravity and a certain temperature and a certain composition. Surface area of the sphere, 4 pi r squared, where r is the radius of the sphere. And then, so for the mass, you want to take that surface area and make it tall, right? You want the density run with from height 0 to height infinity, basically, for the mass. So there's our starting integral. We know that stuff. We just worked out the rho run, so we know that. Right? Yeah, that's the density, and the density is rho naught times e to the minus z over h. So we stick that in there. We do the integral, and we come up with this expression at the end. So it's rho naught ah. Whoa, how simple! Very nice. If we de-simplify that, so for a we put in 4 pi r squared. For h we put in the scale height formula. Then our mass turns out to be this thing here. That's fun. Let's work out some masses. Suppose we have a lunar atmosphere. We know the mean molecular weight of oxygen. We're going to pick a temperature like room temperature, which is somewhere around 289. We know the lunar size. Its radius is 1,700 kilometers. And the acceleration due to gravity there is 1.6 instead of 9.8. The gas constant, we know the density. This is a little bit clever. Let's set the density that we want. Our target density will be about the same as the density of oxygen we're breathing right now, just minus the nitrogen. Turns out this is okay. In fact, the astronauts traveled to the moon on a pure oxygen atmosphere at low pressure. And tragically, they learned this the hard way because they had a fire in one of the early Apollo missions while the capsule was still on the ground because they were using a full pressure oxygen atmosphere, which is actually quite explosive. So you don't want that. But it turns out low pressure oxygen is fine. So let's just target that. And we can figure out the density of that. It's about 0.25 kilograms per cubic meter of oxygen that we're breathing right now. And then here's our formula for the mass. And so let's go ahead and calculate that. And that's 4.5 times 10 to the 17 kilograms. Oh, look, it's a big exponent. The Earth's atmosphere has a mass of 5.15 times 10 to the 18. So it's about 10 times more massive. And if we use this formula with a more attuned mu so that the nitrogen is in there, and we use the Earth's gravity and so forth, we get, instead of the actual number, 5.15, we get a 5.3. And that's only 1% off. So all that temperature variation that happens on Earth, it really doesn't matter. You're good. Undergraduate physics wins again. Okay, so now we know how much atmosphere we need. How long are we going to keep it? And so this part is undergraduate physics, but it's a bit long. So I've skipped over some stuff. The game you play, though, is sometimes called Jeans escape. And the game you play is that you print it in at the outer edge of the atmosphere. Those molecules might leave, but they can only leave if their velocity exceeds the escape velocity of the planet. So the molecule of O2, or oxygen atomic, whatever, might be broken up by then, it needs to have velocity greater than the escape velocity. But that's not all, right? There's some other conditions. So it's kind of a model situation. You have to have it, for example, traveling up and not down. So there's a factor of 2. And also, on its way out, it needs to not bump into anything else. So it needs to be able to escape without collisions. And so in physics talk, that means its mean free path trends toward infinity. It's going to go a long way before it bumps into anything. So for planets, we call this the exosphere, this place where this condition can occur. And that's really high for even for Earth. It's like 500 kilometers up. And they call the edge of space something like 178 kilometers, something like that. Well, the exosphere is quite a lot higher. And it's also hotter up there. So the temperature is more like 1,000 Kelvin than 290. And so enter the Maxwell-Boltzmann velocity distribution. So this is the pinnacle of kinetic theory of gases right here. So we have an ideal gas assumption, and we ask in equilibrium, what is the spread of these velocities? And so here are the curves for, I believe, room temperature and the noble gases from helium through xenon. So at room temperature, this graph plots this formula, which ends in a tailing exponential. And that exponential has a kinetic energy over a KT in that oft repeated little bit of a formula there. So let's take the 1,000 meters per second velocity, which is the x-axis, and this is the probability here. So if we take 1,000 meters per second at room temperature and pretend this is the exosphere out there, then helium will, most of those atoms are speedier than 1,000. So if we have a container that'll let them escape, they're going to escape. But if you look at some of the heavier ones, they will not, right? You look at xenon compared to 1,000 meters per second, that's not escaping, that's staying put. And then you got the ambiguous cases in between. So that's where we zero our attention. So we're going to lose maybe a few atoms, but is that number rate of loss enough to worry about? Okay, so we will assume a temperature of 1,000, and we'll we also can calculate the escape velocity for the moon. It's about 1440 meters per second. Okay, so I am going fast and skipping stuff, but it all works out there. What you have to do is you have to integrate that Maxwell-Boltzmann velocity distribution, but just the tail end, because your escape velocity is way out there on the tail. If you do that, here's the formula we use for this. Your n dot, number of particles that leave per second, is the area times the number density at the exosphere times a parameter called nu. And nu is in fact the gory integral that takes the tail of the kinetic energy over KT part of the Maxwell-Boltzmann distribution. Okay, so more things to plug in, and I won't linger here. The answer, if you've got an n dot, then the time scale needs to be, get your units hat on. We got a total number of atoms, and then then n dot, you should get a time out of that. So here's your time scale for atmosphere loss. And the capital N there, number of particles, we could just take the mass of the atmosphere that we calculated and then divide by the mass of one particle. And so for the moon, that was 4.5 times 10 to the 17. We divide that by the mass of an O2. Then we get this number of atoms around in the atmosphere. And then we work out the numbers. So here's the answer. 120 million years. So in comparison with the lifetime of the moon, 4.5 billion years, it's a very short time. And the moon should not be expected to keep any atmosphere at all. Over the time scale of a human being, that's a really long time. So over human time scales, this is essentially permanent. You will never in your lifetime notice any pressure change due to atmosphere loss. So that's fun. That worked out. So let's address the other problems that might occur. One, where does that oxygen come from? And I started this out by saying, well, we have to, if we're going to have to mine stuff on Mars, we might as well consider the moon. So let's consider mining the moon. And any oxygen we find in the rocks, the idea is that we will vaporize it and then sort it. And then we'll let the oxygen fly free, and we'll keep the metals that are left over. So here's a big list of minerals on the moon. And we'll ignore most of these columns, but do look at the chemical composition. And the abundant ones are in green-ish stuff at the top. Actually, this A is the most abundant, and that A down there at instantite, those are the main minerals on the moon. Capital M is major, little m is minor, and T is trace. So these are the rocks you find on the moon. And if you look at the formula, you find, oh yeah, look, lots of oxygen. So if we broke this top one up, you get 8 oxygen atoms and then 5 metal atoms if you broke that one up. And if you go down here, you look for things, other useful things, I don't want to come back to this slide. So let's just briefly scan for hydrogen, which we'd like for water, and carbon and nitrogen, which we would like to grow plants and animals with. If you scan down here for hydrogen, you don't find anything until way down in the trace elements. There's one, and there's another one down there. If you look for carbon, 0. If you look for nitrogen, 0. None of those things are there. So the moon is really not that, it does take some work to get some kind of carbon and nitrogen to make it really clement for life. But it does have plenty of oxygen. You just have to atomize it and put it through a mass spectrometer and a sorter. I say glibly. I'm sure it's a massive engineering problem, but let's just dream a little bit. So after you separated them and cooled them down, you've got building materials. You've got metals, calcium, aluminum, silicon, magnesium. You've got those to build whatever you need to build with. The best conductor, aluminum is better than copper, right? Solid state people, you want to actually conduct better. And on the moon, you have 6th of the gravity, so you can build cables. Go for it. And then the rest is gaseous oxygen to be released into the atmosphere. How much energy do you need to fuzz out a mineral into its gas components? And the answer is about this number for just about any mineral. It works out to about 4,000 kilojoules per mole. And that will release 4 moles of O2. So 0.128 kilograms of O2 will be released for every 4,000 kilojoules. So we already worked out the mass. So we should be able to work out the energy required to make all that atmosphere. And there it is, 1.5 times 10 to the 25 joules. Okay, for context, the sun outputs 4 times 10 to the 26 joules every second. So this is a small fraction of 1 second of the solar output. Let's see if we can do that with ordinary terrestrial stuff. Oh yeah, I forgot this part. So you also get a lot of building materials, and it is volumetrically smaller than what you started with. but it's still a lot of stuff. It's about 100,000 Great Pyramids. Or it's about 2,000 times the amount of mining tailings that are sitting around the Earth right now. So it is a big digging job. For energy, though, let's suppose that we cover a square of the moon with some solar panels, and we use all that energy. Or I'll assume 50%. So we'll assume we use 50% of that energy to atomize the soil. We turn it into oxygen. So for 100 by 100 square kilometers of stuff, you get about this power output, 6 times 10 to the 14 watts. Guesses? How long does it take to make an atmosphere? Actually, not too terrible. It's about 750 years with this array. That much array, if it were concentrated in one dot, you could probably see it from the Earth, just barely. So it's a pretty big engineering project. I think of this, however, as a bunch of rovers. They'll just be little tractors with a solar furnace, just a reflector, and then also some other solar panels for the grinding and the injecting and so forth. And then there would be a bunch of these things roving around, digging wherever. So you wouldn't even necessarily notice. Furthermore, if that was just an arbitrary 100 by 100 kilometers, you could build more. If you covered the moon in solar panels, it's about 300 times faster, and so that would take 2.5 years. So it could be done. It could be done. Let's move on though. So need to quit at the top of the hour. We need also carbon, nitrogen, and water. So water is hydrogen. So let's see if we can find that. There's a little bit of water on the moon. It's really not a lot. It's good for drinking water, maybe. And we, for sure, at first we want to keep our water very safe under domes. You know, we wouldn't want to let it out for a while. I haven't calculated how much water there might be hidden in those phosphate minerals because I can't figure out how much phosphate mineral there is on the moon. But let's go to the outer solar system. The outer solar system is water. It's almost all water out there. And a whole bunch of, I'll abbreviate it, CHON, so life-giving elements like nitrogen and carbon and phosphorus and all that. And then here again, just arbitrary as 100 kilometers by 100 kilometers. Let's look at one of these outer solar system bodies. Let's pick on Chiron. What's Chiron? Chiron wobbles out between Saturn and Uranus. It's about 110 kilometers in size. It's clearly got a lot of water because it can show cometary activity. So the sunlight shines on it, even at the 1% level where it's located, and it'll boil off into space. And so if we make some guesses as to its mass, which we actually don't know very well, there's a lot of water in it. So it's probably basically half water and half other stuff. And that other stuff is rocks, but it's going to be rich with carbon and nitrogen, whatever it is. So let's imagine we just yank it from where it's at and plop it onto the moon. We'd have a lot of water. That is a huge amount of water. And I like this professional graphics. Here's the Earth where someone has drained the oceans and made them into a ball. So you can see the ocean ball here. You might be able to see just to the right a smaller blue dot. That's from the freshwater ice caps, Greenland and Antarctica. And then you probably can't even see the third blue dot, which is from all the freshwater lakes and rivers. It's below the ice caps there. But then here's my super high-priced graphic on the right showing the moon and Chiron. And you can see it's not, it's sort of comparable. It's about the same sort of thing going on. So That's why I picked Chiron. Well, let's just do the energy. So how much energy does it take? This is a uncommon little energy formula you probably don't know, but the energy of an orbit depends on the mass of the body out there. So let's divide that out, but it also depends on the mass of the sun, the gravitational constant, and little a. Little a is the semi-major axis. So for a circle, that's the radius of the circle. So all we need to do is kind of move this body from its location and inward into the inner solar system. So we just need those two a values. You know those really well. We don't know the mass that well, but we can guess. So if we guess density typical of these bodies out there, then we get about this mass. And then I'm gonna just fly through this. We get a dE there. So energy of 3.5 times 10 to the 27 joules. Okay, the sun again. The sun was outputting 4 times 10 to the 26 joules per second. So this is more energy. This is about 9 seconds of solar output, as opposed to a fraction of a second. So this is becoming a head scratcher now. That's a lot of energy. But suppose we forge ahead and say, okay, so it's more energy than we've ever dealt with before. Most of the reaction mass is going to come from Chiron itself. It's really not, who cares if we consume a good fraction of Chiron on the way? Okay, that's possible. Also, you could use planetary slingshots to decelerate your body, and that's you're going to do it. That's one thing. But just calculating the energy output. Let's suppose we had 100 years to do it. The power consumption would be about 10 to the 18 watts, which is about 80,000 times the amount of energy that we currently use on the Earth. So it really is a big number. So if we're going to do that, we need new technology. We need probably fusion. I mean, it's going to be an interesting job. So maybe let's scrap that for now and use other smaller bodies. So the outer asteroid belt's full of water. There's the Trojan asteroids. Those are a lot nearer and smaller and hopefully more easy to deal with. There's several companies already contemplating mining the asteroid belt. So these are actually company graphics from outfits that'll mine the asteroid belt for you if only you give us $500 billion. There's enough water there, so there's at least 10 times more water than we need for the moon. It's not as much as in the ocean basins on the Earth. I'm thinking we don't bother with trying to control the descent of these things, so we just we shoot things at the moon and let them hit. I mean, you have to be careful. There have to be certain safety guidelines, but I don't really see the harm in it. And you could, sort things before you go. So you could only send just the water and plus the carbon and nitrogen-rich minerals, and that would they would come in packets, and you just wing them at the moon, and then they'd splat down, and then you eventually build up a good supply of lake water. Or just getting speculative, what if you redirected the solar wind? So the sun is outputting a stream of protons and electrons. What if you made a current loop between the Earth and sun and just gently redirected those particles to land on the moon instead? I'm running out of time, so I will skip forward just a little bit. We'll go quickly. So we can figure out the ram pressure. It involves stuff like the mass of the proton, the number density, and the velocity of these solar wind particles. We know most of that stuff. pressure is fairly variable between 1 and 6 nanopascals. And then the particle velocities are, there's kind of a slow wind and a fast wind, but the average is around 500 meters or kilometers per second. And so, so you can work out the number density, and that's like 7 times 10 to the 7 particles per cubic meter. And so you can go ahead and figure out the mass flux rate. And you figure out that it's half a kilogram per second. Kind of interesting. And the idea is those protons would hit the oxygen atmosphere you put on the moon, and they'd turn to water, right? The hydrogen would react with the oxygen, and it would turn to water in short order. And then for all the hydrogen, half a kilogram per second you put in, you would generate about 8 times, there's a factor of 8 multiplier, because H2O, oxygen is a lot heavier than hydrogen. So so for each kilogram, you generate 8 kilograms of water. But even with that multiplier, favorable multiplier in there, if you posit 100 years of this stuff, you get numbers that sound kind of big, 3 billion gallons over a century. But Los Angeles uses up that in about a week. So it's really not that much water that you could get out of the sun. Okay, that's a good idea, maybe. So another one to crash and burn. Now let's crash and burn this one really quick. Can you spin up the moon? The answer is no. The answer is no. So that's just for convenience. So we get a 24-hour day. This is the worst of all. This one works out to 3 times 10 to the 30 joules. Now the solar luminosity was 4 times 10 to 26. This is like 10,000 seconds of solar output. And there's no way we're ever going to do that. For those of you interested in SETI, this is Kardashev level 2 stuff. This is not stuff we can do. For fun, if you did your 100 by 100 kilometer array, it would take you 7 billion years to do this. Okay, so my summary here. So let's see, let's pressurize the moon. I think it's smarter than Mars, be more convenient for travel there. Pretty soon we could be basking lakeside on the moon. In the ordinary Earth-like sunlight. It's cheap, it's convenient compared to Mars. The solar power alone, you notice I did not mention fusion for this stuff. Solar power is plenty sufficient to provide an O2 atmosphere in however many robots you build. If you need it faster, just build more robots. Once you have an atmosphere, it's permanent. It's there essentially forever for human beings. And again, it's scalable. If you want your atmosphere faster, just go do it. Now, at that point, so suppose we have an oxygen atmosphere at low pressure. It's breathable. It's still be kind of chilly on the moon. So you need your parka, but you could walk around other than that. Keep hydrated because the atmosphere will be rather dry. So you will lose water pretty quickly. So if we want water, we probably need to get it from the asteroid belt. Chiron was a bad idea. Spinning up the moon, a very bad idea. Solar wind collection didn't work. And we know this via undergraduate physics. Okay, undergraduate. Lots of engineering challenges, I'm sure, but there was no new physics in there except for the spin up of the moon. That seemed impossible. And so my real conclusion here is undergraduate level physics rocks. You can figure stuff out without I don't know, without graduate level stuff. So physics in general rocks, by the way. I'm not dissing other things when I say that, but undergraduate physics does rock. And with that, thank you. Thank you.
Okay, thank you very much for this entertaining talk. Questions? Good.
Yeah, I've got
at this level of speculation, I've got an obvious solution. Why don't you make some sort of space elevator city straw and just steal your atmosphere and water from the Earth, the upper atmosphere?
Yes, you could. Actually, it's cheap.
Is it
Relatively cheap compared with bringing it in from the outer solar system. I just didn't consider that because honestly, I don't think people are going to go for that. That does not sound like a great idea for we Earthlings.
Well, it's only what percent you said it's like,
Yeah, well, right now it's a good idea because we could use with less global warming, but I don't think that's really a viable solution. No, it's cheaper than bringing it from the outer solar system is to just take it from Earth. It is cheaper.
More questions?
The straw idea, I don't know.
There is a small amount of water ice on the moon, is that right?
Yes.
Much less than what you would require here. But
Yeah, it's there. It's at the poles. Yeah. Yeah, I showed a picture of a satellite. That was the Clementine mission from the 90s. And that spacecraft discovered water via gamma rays. Clever how they did that.
Any further questions?
I have a question online.
Yeah, speak up.
So if we actually wanted to live on the moon, how dangerous is it in terms of like radiation and stuff once you put this atmosphere in place?
It's comparable. So on Earth, we get about half our mutation type radiation from the ground and half from space. And Moon does not have a magnetosphere, but that really doesn't affect either of those things. So basically it'd be the same on the moon as far as I know.
Any further questions online? I can't see if anybody has to speak up. Otherwise, let's thank Guy again for an excellent talk. Thank you.